Bueno, pues para mí es un verdadero placer reiniciar nuestras actividades y es un gusto tener a Mesias. Mesias fue parte del grupo, se creó hace un par de años, de aquí del grupo de química teórica de Sinvestap. Él se unió hace aproximadamente, pues ya casi 8 años al grupo. La idea es que hiciera su tesis de pregrado, de licenciatura, pero de ella no nos pudimos deshacer de él. Se quedó tanto en la maestría como en el doctorado, ¿no? Y la verdad es que ha sido un verdadero placer trabajar con él por muchas razones. Él es físico y bueno, discutir con él la parte de química era bastante enriquecedor, ¿no? Y bueno, el tema que desarrolló durante toda su tesis, tanto de licenciatura, maestría y doctorado, fue que tiene una molécula ante un campo magnético, y es de lo que hoy nos va a hablar, ¿no? Entonces, bueno, se graduó hace un par de años. Su tesis fue galardonada con el premio Rosenbluth, que se le otorga la mejor tesis doctoral de Sinvestap. Y también hace un año obtuvo lo que es la distinción del nivel 1 en el Sistema Nacional de Investigadores, ¿no? Entonces, estoy muy orgulloso de todo su trabajo. Y bueno, Mesías, adelante.
Ok, gracias, Gabriel. Entonces, todo en inglés, ¿no? ¿Lo
Sí, por
mudamos?
favor, porque hay un par de personas o 3 personas que parece que hablan solo inglés, ¿no?
Okay, then thank you for the presentation, Gabriel. It's nice to be showing again this set of works that we have been working in the master and doctoral thesis. So I will be explaining a bit of the works that we have been developing all these 4 years or a bit more, and some of these new papers that we have been publishing in the last 2 years as a postdoctoral researcher. So if you agree, I will stop my video to be focused in the presentation. So we have decided to entitle to this presentation as the molecular magnetic response to quantify aromaticity. So I will be explaining a little bit about the magnetic properties, and I will be trying to focus on the way to use it as quantifying aromaticity. So, oh, sorry, the presentation is again stopped. So, okay. Okay. So then the magnetic fields can be classified from different point of view in nowadays, because of course we have some classical point of view, and we have also this quantum mechanical point of view. So when we are currently working with magnetic fields, we can extract some interesting points from that. For example, the magnetic force are interactions with some materials, and they have a attractive or repulsive behavior. And in the opposite case of the electric fields, the magnetic fields behaves in some way that they have a dipolar behavior. This means that they have a north and a south pole. So there's no an experimental evidence that exists a magnetic monopole. So we have to take this in mind, and this is something prototypical of the magnetic fields. We also know that they are related to charge in movement. So when you need to have an electric current to create a magnetic field. So, and this is the same nature for a magnet, for example. So when you are studying, for example, some electrodynamics or classical electrodynamics, you can find that this can be divided in a diamagnetic and a paramagnetic component. So when someone is trying to solve the equations for a particle moving in an electromagnetic field, or specifically in a magnetic field, one can solve from the classical point of view that, for example, you have a charged particle in an external magnetic field and a uniform external magnetic field, you will get some kind of movement that is an helical movement. So it's trying to move in a clockwise direction. So, of course, by convention, we know that the electrical currents are defined as the opposite direction to the negative charge. So from this point of view, the electrical current will be clockwise. So we can extract from this classical point of view that the electrons move in a clockwise direction because the electric charges are moving always in the clockwise direction for an electron, for example. So we can say, for example, that the electrons are always moving in a clockwise direction if we have an external magnetic field. But this will change when we are talking with from a quantum mechanical point of view. For example, when you have molecules, you can classify the molecules depending on the magnetic response to this external magnetic field, if creating a clockwise direction or an anti-clockwise direction or counterclockwise direction. So we can call to these directions of the currents like diatropic or paratropic currents. So it's called diatropic if the movement of the electron is in a clockwise direction, or it's paratropic is moving in a anti-clockwise direction. So this theory and these magnetic properties are supported in what we call the ring current model. This was introduced in 1915. This is called the Ransome theory of the nuclear magnetic shielding. So this is the theoretical point of view of the NMR experiments, and this allows to explain the chemical shifts in proton. So, but what is the connection with the aromaticity? So the aromatic compounds have some kind of set of properties that if we find these features, we can classify the magnetic like it exhibits some kind of aromaticity. So, for example, it exhibits electron delocalization, high energy stability. Of course, these molecules are prone to are very symmetric, and they exhibit also low reactivity. But the most important from the magnetic point of view is that they exhibit some specific magnetic properties. For example, an aromatic molecule exhibits a diamagnetic response to an external magnetic field. But so we can measure from this way if the molecule is aromatic or it exhibits other kind of properties depending of this magnetic properties. So specifically for aromatic molecules, we can classify it by aromatic if these molecules create a ring current because it has a ring-shaped structure, and when it is exposed in external magnetic field, it will create a ring current depending of the nature of the molecule. So, okay. So, and the connection with the ring current model and electron delocalization is that the electron delocalization is, if you think, for example, in the atomic orbitals, when you have a molecule, these atomic orbitals are combined, creating this kind of molecular orbitals. So the charge or the electric charge can be delocalized around the chemical bonds or the entire structure, as it happens in the in the aromatic compounds. So there are some rules, like the Huckel's rules, that classifies the molecules as aromatic or anti-aromatic. It's called anti-aromatic, depending on the localized pi electron. So, for example, for aromatic molecules like benzene, you have 6 pi electrons. So if you follow this rule, for example, see if you have n is a integer number, for example, if it's 6 and it's equivalent to 1. So this molecule, the benzene, obeys this rule. So in the opposite case, when you have, for example, 2 pi electrons, like this cyclobutadiene, so it's classified as anti-aromatic molecule. So it would be nice that all molecules could be classified depending on counting just this number of pi electrons, but the reality is quite different. So we can take advantage of these other properties, like I don't know, the symmetry or the energy parameters. But in the case of the aromaticity, we can quantify it by quantifying these magnetic properties. So, of course, if you have these molecules with the localized charge that is free to move around the structure, we can compute firstly the current density or the induced magnetic field. So the induced magnetic field is the secondary magnetic field that is created by the current density that is moving around the molecule. So for the case of aromatic molecules, the movement of the electrons is diatropic, is moving clockwise, and the anti-aromatic molecules are moving in the opposite direction, anti-clockwise. So, of course, this direction of the current density also creates an induced magnetic field that can be pointing in the opposite direction of the external magnetic field, or in the same direction of the external magnetic field. So, of course, we can compute nowadays these quantities. Firstly, the magnetically induced current density that can be computed by using DFT or ab initio methods. So we are able to compute the so-called the current density tensor. So this current density tensor allows to compute these vector fields of the current density. In the same way, we can compute this induced magnetic field that is obtained by integrating the current density. And nowadays is implemented in the most of the electronic structure programs. So it is natural to, for example, when we are working with induced magnetic fields or current density magnetic fields, to talk about the diamagnetic and paramagnetic terms as occurs in the classical point of view or in the quantum mechanical point of view. So depending on why is the most important component in the magnetic response, then we can classify this molecule as diamagnetic or paramagnetic or aromatic or anti-aromatic molecule. So for our analysis based on the induced magnetic field, we currently start by using, for example, planar molecules like benzene or cyclobutadiene. When you have these planar molecules, you can locate it in the XY field, in the XY plane, and you can apply an external magnetic field, and then that is orthogonal to this molecular plane. So in this way, under this situation, of course, the induced magnetic field can be reduced to consider only the seat component of the induced magnetic field. So from this point of view, we can reduce the analysis of a three-dimensional vector fields to an analysis of the unique component. So, and we have been also talking about this quantity that is called Nix. The Nix is no more than the isotropic component of this induced magnetic field. So actually, we have been trying to disseminate the idea that the Nix is just like an average induced magnetic field pointing in the three Cartesian directions. So it can be seen like an average quantity of the induced magnetic field. Okay, so we have been working with we start to work with the induced magnetic field specifically because I think it was the easiest way to find a global behavior of the magnetic properties in molecules. So we wrote this program that is able to compute the magnetic response, specifically the shelding, the Nix, or any component of the induced magnetic field, along as an axis that, for example, for benzene here, we have the example of the zeta axis. And we are also able to compute these slides like to see the global behavior in two-dimensional way, but also in a three-dimensional way. So we can compute the volume of the magnetic response in the molecular surrounding. But I think the most important was that we went to the problem to compute the symmetry operations to reduce the computing time in these big molecules. So Gabriel started to work firstly with these small molecules, and the next target it was to increase the size of the molecules. And we had to use some symmetry operations. So of course, this depends on the symmetry of the molecules, but in most of the cases, we can take advantage of that and reduce the computing time. So, for example, in the case of benzene, it's not necessary to compute all these magnetic properties in all this huge grid. So we can use sometimes the symmetry of these molecules. At the moment, we have these options to reduce the computing time, and it has been quite helpfully for reduced calculations in, for example, fullerenes or other kind of symmetric systems. So of course we also were interested on compute the current density, but we need help from other groups in the world to compute the magnetically induced current density. So we start to work with the gimmick method when I moved here to Helsinki in the 2019 and 2020. As far as I remember. So we start to work with the current density. So this is a quite accepted method where we are able to compute the current density from the shieldings as well. So, or the induced magnetic field. So there is a connection between the aromagnetic and the gimmick method because we can compute the same behavior from different point of views. So, for example, for the case of benzene, we can associate the aromaticity to the pi electrons because they are the responsible of this ring current, as we can see in this animation, is flowing diatropically because it's moving in a clockwise direction. And that's the reason why the benzene is explained in terms of the pi electrons. Of course, when we are working with the current densities, sometimes it's important to explain where the aromaticity is coming from, or specifically where the magnetic response is coming from. So when we dissect this orbital contribution, for example, in sigma contribution or pi contributions, we can see, for example, that for the case of benzene, the ring current is completely caused by the pi electrons instead of the sigma electrons, because the sigma electrons are responsible only of local loops and an internal paratropic circulation. But this contribution, for example, from the sigma are weaker than the pi contribution. So when we are summing all this contribution, we can see that the benzene is globally diatropic or globally aromatic due to the pi electrons. So one advantage of gimmick program is that we can compute the ring current strength. So, or sometimes it's called ring current intensity. So if you have a molecule like benzene, you're able to compute this ring current strength by intersecting one chemical bond with a plane. So we can integrate the flux that is coming in and coming out from this plane. So you can see, for example, for benzene, at different level of theory, the diatropic component or the clockwise component is the strongest one. Of course, it does not mean that the paratropic is zero, because of course we have this internal paratropic circulation due to the sigma electrons. But in this way we can quantify the aromaticity, because we are associating one physical quantity to this concept, this complex concept like aromaticity. So keep this in mind, this number, that the benzene is around 12 nanoampere per Tesla. So, and this is a positive number and is associated to diatropicity or aromaticity. In the case of the induced magnetic field, these are the profiles of in the z direction of benzene. So this is the magnetic response computed in the orthogonally to the molecular plane. So you can see, for example, that the induced magnetic field, or the z component of the induced magnetic field, is negative along this field. So this is caused because there is an induced magnetic field pointing in the opposite direction of the external magnetic field. So this is a typical behavior for aromatic molecules. And we are further considering the orbital properties for the induced magnetic field. We can see that again, that the responsible of these induced magnetic fields are the pi electrons. They are the main actors of this shielding or from this magnetic behavior. So when we are looking at the slides and the isosurface in the three-dimensional space, we can see this prototypical behavior for aromatic molecules like benzene. You can see that the main promoters of the shielding, or this is called the shielding cone. The shielding cone, because this is protected, is like the region where the induced magnetic field is opposing to the external magnetic field that is coming in this direction. So this is called the shielding cone of benzene, and we can associate these aromatic properties to this kind of magnetic response. The opposite occurs with the cyclobutadiene that is in anti-aromatic molecules. For example, when we compute the intensity of the ring current or the ring current strength, we can see that the ring current is negative, the opposite to benzene. So then we have a physical parameter to classify the molecules like paratropic or diatropic molecules. So the same occurs for the induced magnetic fields. As we show in the previous figure, you have negative numbers for the induced magnetic fields. In this case, for example, is in the opposite direction, so the numbers are positive for the induced magnetic field. And we have this prototypical magnetic response. I think these figures are quite useful because we can see in colors the different behaviors. So this was the classification, the simple classification of the molecules as aromatic or anti-aromatic molecules. So when we can explore more difficult problems like molecules that contains double aromaticity. This is called double aromaticity because the ring current is caused not only for pi electron, but also for sigma electrons or F electrons and so on. So this is often found in molecules that are metal, all metal molecules or inorganic molecules, and we have more complex magnetic behaviors. So for example, this is the case of the aluminum 2-, when you have this ring current caused mainly, instead of pi electrons, by sigma electrons. So this is the contribution from the sigma electrons, and we can see the induced magnetic field that is caused mainly by the sigma electrons. So however, although it's weaker than the sigma electrons, is also diamagnetic. So this molecule is called double aromatic because exhibit two set of actors working on the ring current and in the magnetic response. So this phenomenon has been explored also in boron clusters. The boron clusters are quite known because they exhibit double aromaticity. They also exhibit sigma and pi aromaticity. But of course, there are more systems where we can be working of double or triple aromaticity. This is the case, for example, with benzene and iodine in the surroundings, where it exhibits a different kind of double aromaticity, because in this case, we have some kind of diatropic circulation here, but this is caused by the sigma and the pi electrons, and this is not recovered in the typical benzene. And we have a sigma circulation in the surroundings. So this molecule is called, we call it in the paper as double concentric aromaticity. So we were exploring also this kind of system like this one, but we were employing several different nuclei in this way. For example, this is iodine, but we have also the case of astatum. So the problem was that when we are working with heavy elements, we have to include some relativistic treatment to the magnetic response. And as you can see, for example, in this case of iodine, we don't have a large difference between the magnetic response. But when we are considering heavy elements, we have a large difference between the non-relativistic level and the relativistic level. So of course, this increased the computing time, but it should be considered in our calculations. So we have been also working with some systems to prove that it's possible to design some kind of interesting configuration as the Helmholtz coils. So the Helmholtz coils is a configuration when you have two loops of current that they have a specific separation between them. So if this separation is the same that the radius of this ring, we can find that when we compute the magnetic field inside this stacked loops is uniform. So we were thinking it's possible to find this same behavior at the molecular level. So we were trying to design some kind of systems to prove this theory, because as we see in the previous slides, the ring current is caused by the pi electrons, at least for organic molecules. So this equation is the classical behavior predicted for the Helmholtz coils. So we were trying to compare the several configurations. For example, we have a 6-membered ring, or a 7-membered ring, and so on. So for example, when we are optimizing these molecules, it is a constraint optimization. We have, for example, for the smallest cases like C6 and C7, the distance is too short. So it creates some kind of chemical bonds here, and it's impossible to get some pi electron. So it was impossible to get some kind of ring current. So we have to move, for example, for the largest cases like CH or C9 or C10. And the interesting was that we reproduce this classical behavior. This, for example, are the, let me move here, sorry. We have here the pi electron induced magnetic field. So you can see that it's quite close to the classical behavior. So in effect, you can see that inside this region, we have a uniform induced magnetic field. So we are proving like the organic molecules behaves from a classical point of view, from the magnetic point of view, sorry. You can see that these pi electrons have a classical behavior. So it's possible to design maybe some kind of system when you can create uniform magnetic fields in between. So the same repeats for larger molecules. This is C9 and C10. We can explore, of course, larger systems. And we reproduce the same magnetic behavior that is quite close to the classical electrodynamics predictions. So we were looking for some examples in the real life, and we found this super fan when it contains this ideal separation. And of course, we reproduce this classical molecular Helmholtz coils behavior. So this is promising. And we have been also working with other problems properly from the magnetic response calculation. One was this considering the core electrons role in the magnetic response. So we were working with the helicins. When we are growing the size of the helicins, for example, we consider the 6, 7, and the 14 helicin. We were checking the core contribution to the magnetic response. And we note, for example, for the case of the induced magnetic fields, that you can see here the numbers, maybe, that the core electron contribution to these systems is quite large. So we were thinking this doesn't have no sense, because the core electrons in principle are quite located in the nuclei, so they cannot create ring currents around the molecules, and they cannot create this induced magnetic field so in a strongly way. So we were thinking, what is the problem? So we were computed some example. For example, if we were linking this feature to the curvature, and we note that it also appears in the planar and in the non-planar case. So what we were noting is that when we have a very large system like these extreme cases, you can see that the core electron shielding is quite big. So at this moment, we didn't know that this is an effect of the methodology to compute this induced magnetic field. So we were looking into the details until we found this paper from Fowler and Steiner, where they were saying that if we have a different way to compute these orbital contributions to the magnetic response, it will create different numbers. For example, in this system, they consider the case of benzene, for example, only benzene, and they see that when we are using this popular methodology as this of the allicins, we have a very large contribution for the core electrons and a very weak contribution if we are computing the orbital contribution in a different way. So then we can associate this problem to the methodology used to compute these orbital contributions. So, but this is the only reports when they say that we have this problem, and this problem is quite often in the papers, because everybody is using this partition for computing the orbital contributions. So we take advantage of some details. For example, depending of the methods, you can have some numbers for the core and the sigma contributions. But what is general for all methods is that you can get the core plus sigma and the pi and the total contribution in the same way, independently of the method that you are using. So we propose to use a simple approximation by removing all the valence electrons from the molecules. For example, you have in benzene, if you have in benzene the magnetic response, and if you want to compute or estimate the core electron contribution, the correct core electron contribution, we can remove all the valence and we can compute the magnetic response. So the magnetic response that you are computed is the magnetic response of the core electrons, taking advantage that the gap between the core and the sigma electron is large. So we started by proving the methods and the reports with Fowler, and we can see that the removing valence electrons approximation is quite close to the numbers of Fowler. So we were able to compute the magnetic response of the core electrons in all the three-dimensional space, and we can see the difference between the methodologies. But this is the correct one, at least the approximation of the correct one. So this also give rise to the calculation of the atomic. This is called the atomic current of the nuclei currents. So we were able to compute the ring current, and it's flowing close around the nuclei, and it's about 4 for the case of carbon nuclei. So we were able to fix the problem with the previous reports. For example, in the case of fullerene, the interpretation can be completely different if we are using one methodology and if you are using other one. So when we introduced this removing valence electrons approximation, we were able to solve that big deal. So in the case of LatinXChem, you can see that you have different, completely different behaviors. So we were also working with very large molecules. So we were looking for an option to approximate the system. And we found this pseudo-pi model. This pseudo-pi model was also introduced by Fowler when the model works in this way. For example, you have one organic molecule or one all carbon molecules, you can approximate the pi electron magnetic response by removing all the hydrogens in the molecules and replacing all these carbon nuclei by hydrogen nuclei. So this is a quite simple approximation, and you can compute this magnetic response and you will reproduce accurate with a high accuracy the pi electron response. So here we have some previous reports of the level of accuracy and also from the computing times. You can see for a typical pi electron calculation compared with a pseudo pi calculation. So we were trying to expand this methodology to planar and non-planar molecules, and we choose all the system. So we were able to compare the accuracy of the level in the three-dimensional space. And you can see, for example, that for aromatic molecules, you have a quite accurate, this is the true pi electron, and this is the pseudo-pi approximated pi electron magnetic response. So you can see that this is a good approximation for that. So of course, we are able to compute the magnetic response then for molecules, for very large molecules that in the normal methodology, you have to compute a very demanding calculation. So we were trying to expand this methodology and compute the ring current strengths for these large structures. So for example, this typical calculation of the total, for example, in the case of Kekulin, takes about 5 hours, and in the case of the pseudo-pi model, it takes 2 seconds. So it's quite useful to compute that, and you can see the similarity between the total and the pi, because of course for organic molecules, the pi electrons are the main actors of the magnetic response or the aromaticity. So I think the great achievement of this paper was to introduce the methodology for non-planar molecules, and we expand finally for systems like LatinXChem and for toroidal carbon nanotubes. So it was quite useful to compute the magnetic response in this very large structure, in nanostructures, because in other way it will be impossible to compute. So we can see, for example, this toroidal carbon nanotube, that they create strong current densities flowing in this direction. So this molecule is globally aromatic. So maybe we can introduce other words like nanoscale aromaticity. So, and you can see here the induced magnetic field, and everything was computed by using the pseudo-pi model. Of course, we have been using lately this model to compute other systems like the infinity. You can see, for example, that using the pseudo-pi model is able to give a clear idea of the movement of the pi electrons. So you can see, for example, for this interesting molecule, that it contains 2 non-intersecting ring currents. So this molecule is aromatic, but it does not have intersecting pathways of the current density. This is quite weird. So this was published in PCCP using the model. And also, of course, compute the pseudo-pi model is quite useful when you are working with this large structure, because you can create these beautiful animations. this was highlighted by Chemistry World, maybe because they liked this animation. Of course, we have been also applying this pseudo-pi model in very large structures like nano onions, when you have these concentric fullerenes, when you have increasing the size and the size is getting large. But the problem is when you compute the total magnetic response, these calculations are quite demanding. So it will be impossible to do it without this model. And we can see that, for example, in the case of nano onions, you have the same behavior as the individual fullerenes. So the magnetic response is just the sum of these layers stacked in between. So we have been also working with new three-dimensional aromaticity with clusters that they are fluxional. For example, we have this cluster with aluminum, and here we have a boron triangle. But interesting in this system is that it contains some kind of current density flowing in the true space. So this molecule can be called a true three-dimensional aromatic molecule. Sorry, maybe this is stuck. Okay, and we have been also lately with this other kind of system when you have planar pentacoordinate atoms. But the interesting here is that we are applying or removing valence electrons to compute the ring current strength. For example, you can see that when you are using a ring current plane to integrate the ring current intensity, we are with this problem with the nucleus inside. So we have to remove the effects of these core electrons in the middle. So when we are removing all these core electrons, we can achieve a rather good approximation of the valence ring current. So you can classify in this way these molecules, because when you are computed the normal ring current strength, you can see that you have very large numbers, but this is caused by the noise of the core electrons. So this is in preparation, is in peer review, and we have also systems with non-benzene rings. For example, we have other molecules, organic molecules, when we have been computing these ring currents, and these molecules is quite interesting because it creates a diatropic circulations with not benzene rings. So lately we have been submitting this work with this new kind of family carbon nanotubes when you have these non-benzene rings, and this is able to create also diatropic currents, and these are like new boat-shaped aromatic molecules. Sorry, the computer is quite slow. So we expand this calculation for very large structures, but we are not using benzene like rings. So we are using this new family of rings. So we got also extremely strong molecule, extremely strong ring currents in the nanoscale. Finally, we have some concluding remarks that we have to compute the magnetic response not only in a local way, for example, by computing magnetic response only in an axis. So we are trying to expand the calculations in the molecular surroundings to understand the global behavior of the aromaticity and the global behavior of the magnetic response. So for the case of the heavy elements, I think the most important lesson is that we have to introduce some relativistic calculation or spin orbit considerations. So it's also important to consider the level of theory when we are computing NMR calculations. For example, this is a new finding because we are increasing the size of the molecules, and we have been trying to find the correct functional to compute all these properties, because it can be changing from level to other levels. Finally, the orbital dissection is a problem if you are not using correctly. So we are trying to propose new solutions to popular methodology. So like this, removing valence electrons. Of course, the theory of large molecules can be useful using new models like this pseudo-pi for the case of organic or carbon structures. But of course, this is our next step to be creating molecules larger and larger and find what are the properties at this level. Of course, the design of new arrangement like the Helmholtz coils can be able to create interesting devices from the electromagnetic point of view. I want to say thank you to Gabriel by giving me the opportunity to work in his group all these years. And of course, to the professor Dennis here, where I have been working the last 2 years in the University of Helsinki. And of course, all collaborators and friends. I want to say thank you, of course, to the MONI Mexico by Conacyt, and the Finnish MONI that is coming from the Magnus Ehrnrooth Foundation. So I think thank you if I have been so fat, sorry. Thank you.
Thank you, Mesias, for this very nice talk. So if somebody have any questions, so please.
Okay, I think everybody's sleeping or something.
It is. So I have a question, Mesias.
I have a question, sorry. Okay.
Adelante, Faustino. Faustino,
Well, in the case of the Helmholtz array, you have the currents in the same direction. Is it possible to make a system in which the two rings, I mean the real chemical rings, has the current in the opposite direction, not in the same as in the previous case that you show? Is there any system in the real system that has the current in the opposite direction in such a way that you get a magnetic bottle?
Yeah, actually, it's quite interesting, this question, because I have been thinking on it when I was working with the Helmholtz configuration. But the problem of the advantage, depending on how you are seeing this phenomenon, is that when you have, for example, two anti-aromatic rings, I mean, when you have these paratropic circulations, when they are approaching, they change their magnetic behavior. So it becomes in a global aromatics. So in this way, they start to create this circulation in the same direction. So
okay.
they start to interact by their orbitals. So that's the problem, and they always create this kind of
to follow the same
behavior.
direction.
Yeah,
Okay.
that's a problem, but it will be super nice that a system broke.
To create a magnetic bottle in a molecular system.
Yeah, it will be nice, but at least I don't have idea at this moment.
Okay, thank you.
Muy bien, Mesias. So somebody else has any question? No, Gustavo?
Hi, Mesias, very nice talk. So thank you for everything, very interesting. So I had a question, if I can understand well, because my internet is unstable right here, but you use mostly DFT for the description of your systems.
Yeah.
And I was wondering about the dynamic correlation effects of the electrons on this aromaticity under these models.
Yeah, I have been working lately with MP2, for example, and the numbers are quite similar to DFT. So actually the theory is implemented in DFTs, but there's no problem for computing with other level of theory. The numbers are quite similar. We don't know, maybe with inorganic systems where the correlation is stronger, but I think this is a field that is in constant developing. Yeah.
Yeah, probably with MP2 would be very similar because you are contemplating just static correlation, right? But with CAS, SCF, or I don't know, CIS methods would be a little different, probably. I don't know.
Yeah, actually, I think the new field in aromaticity is to work in the excited state. So in the excited state, DFT is crap. So probably we need to move to this methodology. There are some results using gas ECF, but the problem is that these calculations are quite expensive. So we can compute only in one point. And so you can imagine if you work in the three-dimensional space, it will be a headache to compute. But we have to continue on that.
And it gives me to another question. So I know that some aromaticity systems and some aromatic systems are also anti-aromatic on the excited states. Have you ever tried these calculations over under TDDFT almost?
Yeah, I have been working with some stacked organic molecules in the excited state. I think you can trust on them, but not much, because we have been noting that this in the excited state, the geometry plays an important role. So when you move only maybe 0.5 angstroms, the behavior is completely different. Even the ring current strength changes dramatically, for example, in 10 or 12 nanoampere per Tesla. So you have to be very careful with that, because if we are trying to measure a very detailed quantity, it will be difficult if you are changing from one description to other description. So, of course, we will be trying at least for simple molecules, but we don't know in the future. Yeah.
Okay. Thank you very much.
Thank you.
So, may I ask a question?
Thank you,
Gabriel? Gabriel?
Please, Michael.
Okay, yeah, it's about, these calculations that you did, Mesias, about fluorines. So in principle, you get this response, but in the particular case of fluorines that you studied, they are not aromatic. This C240, I mean, according to Hirsch's rule, it is not aromatic, or the C540, it is not. I mean, you have to oxidize the C240, at least you have to remove one electron to get to make it aromatic. So my question is, okay, it seems that just to have the magnetic response is probably not enough to decide if something is aromatic or not. And in particular, in the case of nanotubes and these new nanotubes that you show us, I mean, the only thing you have to support the aromaticity is the ring currents, or you have maybe more data, I don't know, other possible indices of aromaticity or other things. This is my question. Thank you, Mesias. Very nice talk, by the way. Thank you.
Thank you, Professor. Yes, I think I have been skipping this comment, but of course, this is only one phase to compute or quantify the aromaticity, only using the magnetic properties. But of course, there are some examples where the magnetic response is not enough, and maybe there's there are a lot of options where we can compute, for example, the energy indicators or aromaticity or geometric parameters. In the case of fullerenes, these large fullerenes, all these systems that we have been working do not satisfy the Hirsch rule. So that's the reason why we start to consider the magnetic properties, because in this case it has been quite useful to use the magnetic response calculations. But maybe the main conclusion from this system is, for example, when you have C16, the typical fullerene, the most famous is that it's like a particular case when you have this 5-membered rings so close. So when you compute it, it's practically paratropic. So when we are increasing the size, these 5-membered rings are so far away from them, so that the 6-membered rings, that they are able to create a stronger diatropic current density there. So globally, we can consider it like aromatic molecule. But of course, this depends of the orientation sometimes of the external magnetic field. So in systems like large fullerenes, the magnetic response helps, but maybe it's not enough to classify it. At least from the magnetic point of view, it's easy to classify it, but not for all this global description of aromaticity. Aromaticity is a multidimensional problem, as you say.
Okay, thank you very much, Mesias. Nice talk.
Thank you.
Muy bien. Somebody else has any question? So I have only a couple of comments or questions. So the first is that in principle, you compute the tensor, a tensor in any point of the space, no? But finally you contract this tensor and you obtain some vectors, and or even worse, you obtain some scalar fields. So do you know if it's possible to obtain more information about this tensor and maybe to understand other properties of the molecules?
We don't know. In the past, we were trying to understand what the anisotropy of the Sheldon tensor means. We have been trying with other quantities to try to extract some kind of information. Maybe can be information that is not directly related with aromaticity, maybe with other kind of properties. But at the moment, only these Cartesian coordinates, Cartesian components are useful for the magnetic response analysis focus on the aromaticity. Maybe we can extract some other quantities for, I don't know, maybe electric properties or symmetry properties, or this new field of the vortex on the topology of the currents or the magnetic response. But at the moment, I'm sure that we can extract more information, but we don't know what does it mean.
Yeah, because when you contract any tensor, you will lose some information. So I don't know if we can obtain more information or how to interpret these behaviors. No? And my other question, I think it's quite important to mention what are the limitations of for this new pseudo, not new, but this pseudo pi model, no? Because it's working quite well for big molecules, but there are some restrictions, no? That it's important to mention. So it's not working for all the systems, no?
Yeah, actually, it's always the reviewers' comments that they are saying that, of course, you have to test in other systems. In a first glance, it does not work for molecules that they are not well sp2 hybridized. So maybe the problem is with system that has triple bond or single bonds, so or quite distorted structures. So in these cases, we cannot apply the pseudo-pi model. For example, this system from Michael is not able to be reproduced by using the pseudo-pi model, despite it is a carbon molecule.
Muy bien. Pues muchísimas gracias, Mesias. Thank you very much. Con eso
Thank you, Gabriel, for the invitation.
Damos por terminada nuestra primera charla de este año. Y bueno, y ojalá nos sigan acompañando. Y nuevamente, gracias a todos por conectarse. Hasta luego.
Hasta luego.
Thank you, bye-bye.
Bye, bye, Miguel. Gracias por conectarte.
Bye-bye.